Thanks everybody for tuning in. And this time we have the pleasure of having Lukas Schneiderbauer from University of Iceland, who is going to tell us about semi-classical black hole complexity. So Lukas, please take it away.
Let me start by thanking actually Ro, Hugo and Johannes for organizing this very nice seminar. Very good idea, by the way, to do that. And also for giving me the opportunity to present some of the work I have been doing together with Vatse Sibisma, a postdoc here in Iceland, and my supervisor Laurus about semi-classical black hole complexity. And the material I want to present is based on a paper that recently made its appearance, actually 2 days ago, into the archive. So have a look at this one. So what I will talk about holographic complexity today as an additional entry in the holographic dictionary. But before I'm actually going to tell you what our goal is exactly, I want to actually before review very briefly some concepts we are going to need to formulate that. And after that, I will actually proceed to explain to you what we actually want to achieve here. So bear with me in this time. So first, since I'm talking about holographic complexity, I want to spend a few words on what complexity actually is, or what we understand under this notion. And so we start by imagining actually a quantum computer modeled by a quantum circuit. And a quantum circuit usually is described by a finite dimensional Hilbert space. So we are in this setup now. And so what is actually a computer? It's basically its building blocks, a collection of gates, as we call them. So these gates are modeled in our case by just unitary operators, which act on states in this Hilbert space. So, and these gates basically, as I already said, are these building blocks of the computer, which the computer computes with. And so if this computer is of any good, then we actually want to demand that this collection of gates, which is the computer, should actually be good enough so that we can actually reach, or we can actually calculate or compute with this computer everything we want in principle. So we demand of this gate set what we call to be a universal gate set, that we can actually reach from any given input state, psi naught, any output state, psi, essentially. So that we demand of this gate set. And now we can just simply define complexity of a state psi of interest here with respect to some reference state as the number of gates I actually need to go from one state to the state of interest we have. And of course, there are more possibilities to actually go from one state to another one, where the complexity should be the minimal amount of number of gates I need to go from here to here. Okay, this is all about what to say about this quantum computer complexity. Now let me mention black hole complementarity. So, which was basically introduced in the original paper in '93 by Susskind, Tolasis, and Uglum. And black hole complementarity states that that the dynamics of the interior of the black hole for an outside faraway observer can be equally well described by a quantum mechanical system, which is thought to be living on the stretched horizon. So we will talk about the stretched horizon in a little bit more detail later on, but for now we can think of the stretched horizon just as being some membrane being not or very near to the actual event horizon of the black hole. So in order to make this work, there are a few ingredients which we need, or minimal assumptions. So first of all, if we want the Bekenstein-Hawking entropy of the associated to the black hole actually be realized by some microscopic theory, then in order for the quantum mechanical system to support a state which can exhibit this kind of entropy, we need at least a number of degrees of freedom that matches this entropy. So what we will assume here is that the quantum mechanical system actually has the number of degrees of freedom of order of the Bekenstein-Hawking entropy. So then there is a time running on the quantum mechanical system, and this is going to be associated to the Rindler time on the geometry side. And then there's another property of black holes, namely the fast scrambling property, which was expanded on by Zecchino and Susskind in 2008, and also follow-up papers on that. So, and this seems to be universal properties of black holes. So in order for the quantum mechanical system to exhibit these kind of fast scrambling properties, we actually assume here a simple model, namely a quantum circuit. And then we assume that the Hamiltonian that acts on the states is actually k-local and all-to-all, which means k-local means that, so in this graph, in this plot here, we have a quantum circuit which actually has 1, 2, 3, 4, 5, 6 degrees of freedom only. But by the k-locality mean that the Hamiltonian acts actually with gates that involve k degrees of freedom at the same time. They don't have to be necessarily next to each other. They can also be somewhere, but they should do it in this way. And all-to-all means that the Hamiltonian in one time step should actually involve all the degrees of freedom on this quantum circuit. Okay, so this is going to be the minimal model which we're going to have in mind for our quantum mechanical system on the stretched horizon. So now we can combine the notions of these black hole complementarity and complexity, and actually ask the question, what is the complexity of a state on a quantum circuit corresponding to a black hole? So we will have in mind this model here, which has the number of degrees of freedom. It has around s qubits. It has a k-local and all-to-all Hamiltonian. Now, what follows from then is that, as I already said, at each time step, the Hamiltonian acts actually with k-local gates, and it has to be all-to-all. That means that at each time step, we actually have around s over k gates that act each time step. So that means if we start with some arbitrary reference state, let's say at t equals 0, and we evolve this state with this Hamiltonian, and since this Hamiltonian will act with a number of gates that is proportional to s, also the complexity of the state will increase per time step with a number that is proportional to s. Now, of course, this cannot go on like this forever, because at some point we might hit the state that actually has a shorter route to it, which would be a lower complexity. But it actually can be estimated, and this was presented, for example, in the lecture note of Susskind in 2018. Probably this information was there earlier, but this is where it's nicely summarized. So this was estimated that this goes on for a time which is of order exponential of the number of gates, number of degrees of freedom, which is a very long time if S is appropriately large. So now, if we want to relate this complexity growth, this is now proportional to S if we express it in the circuit time. Now, if we remember that circuit time was actually related to Rindler time, and we wanted to relate the Rindler time to the Schwarzschild time, which comes in a factor of T, where T is the temperature, then that actually means that the complexity should grow proportionally to S times T, where S is the entropy or the number of degrees of freedom here, and T is the temperature. And this is kind of the famous formula, which is checked all over again. So because now we can ask, okay, now we have this reasoning on the quantum circuit side, but now we can ask, okay, is there actually a holographic dual to this notion? So could we actually compute this complexity purely by using the geometry side? And there were basically also two proposals that came up in 2014, the first one by Susskind, was that this complexity should be somehow related to the volume of the black hole. So this is essentially what we are going to talk about today. Then there is another conjecture came out 1 year later, 2015, also by Susskind, Brown, Roberts and company, which supposedly relates the complexity to the action evaluated on some patch of space-time, which is called the Wheeler-DeWitt de patch. We will also have something to say about this, but not in this talk today. So we will concentrate on this proposal. Now, there are already a number of papers in the literature about actually carrying out these volume proposals for various kinds of different black holes, also in different dimensions. And what basically the result is that this, for all reasonable examples I know of, that this relation C dot is proportional to S times T is basically obeyed, at least late times. So what we want to do is to go one little step further now and actually check whether this proposal still makes sense when we go in a dynamical situation, namely when the black hole is actually evaporating. So this is the basic question we have. Like, if we compute this proposal, this volume, will it still exhibit a growth that is proportional to S times T? This is the basic question. And so to do that, we...
Maybe a short question
yes.
in between. So
yes.
Since you consider like an evaporating black hole, do you hope or aim for also asking questions related to like the information paradox or unitarity problem related to black?
Well, the model we are considering doesn't really go that far. So, I mean, you will see later on how we will build up this model. So not we, but how it was done in the history and how we will use it. But in these kind of models, you basically include first order quantum corrections to get some kind of evaporating black hole. But you always have the problem that at some point the black hole has shrunk enough so that the quantum corrections actually become strong outside, so that you actually can't trust this particular model anymore. So I don't think we can actually address anything reasonable about that, because everything the model will tell you, it's not trustable.
Yeah.
Does this answer your question?
Yeah, thanks.
Okay. Yeah. Okay, so as I said, we want to go to this evaporating black hole, and to do actual computations, we go to a 1+1 dimensional setups where where there is an existing model which models an evaporating black hole. More details to that later. But before we actually can jump to the evaporating black hole in these two-dimensional models, we should also do our homework, basically, and see if these kind of conjectures in these models also make sense in more easy setups, like the static classical setup, like the eternal black hole, and then a dynamical setup, still classical, like the classical gravitational collapse, and then we will go to the actual evaporating black hole by adding quantum corrections. And we will see that this homework will not be for nothing. We will actually learn valuable lessons in the classical cases already, which we have to apply to the evaporating black hole then. Okay, so what I'm gonna do now, I will introduce the model, and basically we will go through all these solutions, and I will tell you the results of our computations. So the model we are gonna use originates from a 4-dimensional gravity Dilaton model by spherical reduction to 2 dimension. So what we are going to have here. So we have the G here is, as usual, the determinant of the metric. The phi is the dilaton. R is the Ritchie scalar. Now here we have a kinetic term for the dilaton and the potential. So lambda is a constant here, and it is a length scale. 1 over lambda is a length scale that is basically set by the magnetic charge of the high dimensional parent theory. So this is the length scale that actually we refer to as 1. We measure everything in this length scale here in the future discussion. And here we also have some scalars f, which model the matter fields in these models. And we have a number of n of those. And yeah, you see just the usual kinetic term. So this model is called this is the classical version of the so-called CGHS model by Callan, Giddings, Harvey, and Strominger in 92. And what will be important for the future is that, so in the 4-dimensional interpretation, this e to the minus 2 phi factor can actually be identified with the area of the transverse 2 sphere in the 4-dimensional theory in Einstein frame. So just to keep that in mind for later on. Okay, so now we can take this action and compute equations of motion and then present some solutions of this. And one of those solutions we are interested in is a 1-parameter family of solutions, namely which we interpret or are interpreted as the eternal black hole solutions. So how does this look like? So we switch off the matter fields. So we have no matter fields around. And then we can describe everything in a coordinate system, which we refer to as Kruskal coordinate system, where the conformal factor of the metric is actually equal the dilaton factor. And these are light cone coordinates. And the solution looks like this. So the dilaton factor, the exponential of minus 2 phi, is some m, where m is a positive parameter, minus these coordinates here. Now you can immediately go ahead and, for example, calculate the Ritchie scalar in this with these ingredients, and you will find that for some lines here where x plus and x minus is actually equal to m, the Ritchie scalar will blow up, and these are exactly the lines that will be interpreted as the black hole singularity. And so now you can go ahead and even draw a Penrose diagram of this geometry, and it will look like this. So it will actually look exactly like a Penrose diagram in a 4-dimensional asymptotically flat black hole. So here we have the global event horizons. We have a black hole singularity here and a white tail singularity here. And yeah, that's it for this solution. So now what we want to do is we want to take the solution and apply the complexity equals volume proposal, which I haven't actually talked to you in detail what that actually is. So I will do so now. So this picture becomes a little bit more busy, but we will still manage. So again, we have the Penrose diagram here. Here the black hole singularities, the horizons, here and here, and the white hole singularity. And now what this CV proposal actually tells us is that we should draw some anchor lines somewhere in the space. We have here one on the right side. And for convenience in our calculation, we choose anchor lines where the dilaton is actually constant. And it also instructs us to draw an anchor line on the opposite side of it. And then we have some anchor points here, which parameterizes actually our time. And we do so on the left side as well. And then we connect these 2 points by a volume slice. And we ask, what is the extremal volume that connects those 2 points? And then we take the volume of these slides, and these are the volumes that should be related to complexity. So we have 2 parameters here, TR, and this is a typo, sorry, it should be T left. So we parameterize the volume by these two numbers. And okay, these numbers are arranged now so that as I increase T, we will move the point upwards. And sigma A is a fixed number corresponding to which anchor line I choose, which I leave open for now. So now there is the question, okay, in 2 dimensions, what is actually the volume? So if you would say, okay, a volume, usually it's a codimension 1 hypersurface. So in 1 + 1 dimension, that would mean actually we just have a 1-dimensional curve, and which we have to extremise. And as we know, 1-dimensional curves which are extremized, where the length is extremized, are actually geodesics. Now it turns out that if you do this calculation with this prescription, it will actually give something that doesn't fit at all with the proposal that this should grow like S times T. So what we do actually to fix this is that if we remember that this theory actually comes from a 4-dimensional theory, then, and we would write the volume down of this 4-dimensional theory, which would be a codimension 1, that means it's a 3-dimensional volume, and we would get a factor of area here, which exactly is given by this e to the minus 2 phi, which I told you before can be identified with the area of the higher dimensional transverse 2 sphere. So, okay, if we try this, which would be a volume in the 4-dimensional theory, then it turns out that it actually works much better. So after some calculation, we can actually, the model is simple enough so that we can actually write down explicit solutions for this. So we have now the volume, which is the volume of such a slide, parameterized by these 2 points here, TR and T left. It turns out that this actually just depends on the sum of those. So there are 2 important points here, or one important, like there's one term which is linear in this time here. So we have m/2 times TR plus TL. Okay, then we have some constant, which is obviously dependent on where this anchor curve is, because if I move this anchor curve further to the left, then the volume actually might become bigger. And then we have some contribution that actually is not relevant if you consider late time behavior. So now the important point is that we have this linear behavior here, which we want to have, because S times T in this model would be M. So this would satisfy this prediction that the volume growth should be S times T. But one important point to notice is also for later considerations that this growth actually does not depend on the sigma A. So it does not depend on where this anchor curve actually sits. And this we will use later on. So to summarize, there are 2 important points which we learned here. One is that we actually have to include this area function here to make it work. And the other one is that the growth in this case does not depend on these anchor curves on the left and right hand side. Okay, so we will use this information now to go to the next step, to go to the gravitational collapse. So a dynamic situation. And so we have, I present here, so what we start with is we have now an incoming matter shock wave, which is supposed to create our black hole. So, and for simplicity, we focus on a very thin shock wave of infalling matter, which in this Penrose diagram is described by these red lines here. Okay, so what this does, actually, we can write down solutions again. So we start out with some vacuum state here, which is described by this formula before the shockwave comes in. Then the shockwave arrives, flies in here, and actually creates a singularity. And this singularity persists forever because it's classical. Okay. So now we study this gravitational collapse situation with this CV prescription. And what I'm going to present now is actually not the Penrose diagram, but the actual Kruskal coordinates, which I was describing to you earlier, how this diagram looks there, because we will need it later. So what is here, this blue line is the anchor curve, which we saw previously also as a blue line. And as I move this point, T, this T is going to increase. So now what I'm going to do, I take such a point and I connect a volume slice. And the exercise now is to actually extremize this quantity now of these particular volume slices as I go along this parameter. Here again, you see the shock wave coming in. So here again, you will have some vacuum state, and which creates a singularity here. So now the important point is the following, that as in the static case, if we look at the late time growth of what we're calculating, this does not depend on the location of the anchor curve. Okay, we could move the anchor curve a little bit here, a little bit there. It doesn't matter for the late time behavior. But the difference is now, since we have a dynamical situation, that the onset of the growth rate, so here we have vacuum, so there should nothing be growing. It should only start growing when we actually have the black hole created. And the onset of this growth rate actually does depend on the location of this anchor curve here. Now, what I'm going to show you now is a plot which describes two different situations of this anchor curve. One, where this anchor curve is actually at the stretched horizon, where now we define the stretched horizon, as I said earlier, as a membrane that is not far away from the event horizon. And in this case at hand, we define it to be outside the event horizon with the area of the, which obeys that the area of the stretched horizon is just the area of the event horizon plus 1 unit. That's the definition. And if you draw this in this diagram here, you will get this particular blue line here. So now I will compare a calculation where you would do it with an anchor curve that is far away and where the anchor curve is actually agrees with the stretched horizon. So what you see here on the x-axis is the time t, which runs here as you move upwards. And on the y-axis is the volume growth rate. So how fast does this volume, which I calculate on of this slice, actually grow? Now it turns out that if I calculate this for an arbitrary anchor curve outside, that the growth rate actually starts growing when the anchor curve crosses the shock wave here, which actually would mean that as soon as the shock wave is released, the complexity immediately starts growing, although there is actually not a black hole there yet, because it's only created at a later point. Now, in contrast to that, if I actually now take the stretched horizon and would do the same calculation, I would find that it's actually 0 for a very long time until essentially at t equals t2, which is this point here, which is exactly when you would say that the black hole is actually created. So we see here that this leads us to believe actually that the correct anchor curve in this situation is the one that starts growing at exactly the time t equals t2, which is when the black hole is actually created, and not very long before.
Sorry, a question. Can you explain a bit more what's the significance of time? I mean, maybe not what's the significance, but what's the precise definition of time t2?
Yeah, t2 is when the stretched horizon actually. So in this coordinate system, times of lines of constant time are straight lines. Okay, so this, for example, would all be constant time. So t2 is then exactly the point where the stretched horizon actually crosses this line here, the infalling shock wave, which would also be the time the guy actually sees here this black hole forming.
I'm not sure if this is I'm a bit confused because this doesn't look particularly coherent in the sense that, like, you say, okay, there is some particular constant time fluctuation of this black hole solution, dynamical black hole solution, right? And I define T2 as a time at which the one of these time slices crosses the stretch horizon, right? So
yes,
yes. I typically use, like, say, causal relations, maybe even only causal relations to define, like, maybe like some relate the time on the boundary.
Yes, so
the boundary, but you have some surface, and the time in the bulk.
Yeah, so what I can say to that, like, okay, not in the classical picture, but when we actually go to the semi-classical picture, then there will be Hawking radiation turning on at some point, which the outgoing guy can measure. Okay.
Okay.
And this will also correspond to this time.
Okay.
You're right that in this particular case, it might maybe not necessarily be this time.
Okay, let's wait till you discuss Hawking radiation then. Thanks.
Yeah. Okay. Okay. Yeah. So let's go to this evaporating black hole case, where we add quantum corrections. This was already done in '92. So this part here is still was still studied by CJHS. So what one does here is one includes quantum corrections corresponding to the matter field sector, so the Fs which we had. So we integrate out the quantum fluctuations of these guys. And then in principle, of course, one also would have to include the quantum corrections of the gravitational sector and the Dilaton sector. But in order to avoid that, we do the trick that we assume a very large number n of matter fields, which then supposedly these terms suppress the quantum corrections corresponding to the Dilaton gravity sector. Okay, so these quantum corrections corresponding to the matter field sector is basically determined by the gravitational anomaly of the energy momentum tensor, and which is this Polyakov term, like here. And so this was already studied by CJHS. Now, what was done in '92 as well by Russo, Sask, and Tolas is to add another term, some kind of counter term of this form. And this basically what it does is it keeps a classical symmetry which was there, which was generated by this current here. Where rho is associated to the conformal factor, to keep the symmetry. And it turns out that this actually makes it easier to write down solutions. So, so this is what we're gonna adapt here. So we view this as some quantum effective action at first order. And now what we do with this action is we just treat it, we just minimize it and equally like get equations of motion and solve them.
So sorry, I joined a bit later. Can you remind us what's not?
Say again.
I joined a bit later. Can you remind us what's S naught?
S naught. Sorry. Sure. That's the classical CGHS action, which we saw before. This one.
Okay.
So yeah, okay. Okay, so now we study again an infalling thin shock wave of this form here. And here you see a Penrose diagram. So this shock wave would come in here. And in order to write down the solutions, it's actually more convenient or appropriate to define this field omega here, which is this area functional from before, plus some corrections. And then again, in these coordinates, the conformal factor is basically given by the dilaton. And then you actually can really write down the solution for this omega here. It looks a little bit more complicated, but still very easy compared to everything else, I would say. So here we have again some vacuum situation, and then we shoot in these matter fields here, and we create a black hole singularity. But now due to Hawking radiation, which also back reacts to the geometry, the black hole shrinks, and it will at some point be evaporated, basically. But yet again, we have to be careful here, because so in order for the semi-classical approximation to make sense, we need that the mass of the black hole, m, is first much larger than n, and also n should be very large, right, to have this approximation in the first place. So, and inevitably, it will happen that when the black hole evaporates, goes through this stage, it becomes smaller and smaller and smaller. At some point, even if we start with a large black hole where the quantum corrections are small at this region, for example, we will eventually run into a region where the quantum corrections become strong, and where this model is not trustable anymore. So there will be some region here which doesn't tell us a lot. I mean, this model will give us an answer, but it's not an answer we should trust, I would say.
So another
Yeah.
Question about notation. So what is capital omega?
So omega is defined by this expression here. So
okay,
it's just a rewriting of, it's just more simple to write down solutions if we define the omega by this case, by this field.
So what you do is basically, I mean, just to get the feeling. So what you do is like you solve equations of motion coming from the action that you had that was including the semi-classical corrections.
Yes.
On the right hand side, you add the stress tensor of the form of the boxed expression on the slide that you just moved. I mean, like, yeah. I mean, like on the right hand side, you have this T++ as the component of the matter stress tensor, right?
Yes.
And you solve for the conformal factor phi.
Exactly. Or for omega in this case.
Or omega, okay.
Yeah.
And the solution for omega is given here. Okay.
Is given here, and basically so there's some subtlety here to invert this formula. So there are actually values of phi or values of omega for where there exists no value of phi. If you just to try to invert this formula, so there is a critical value of omega, and this critical value of omega you see actually here. This is to be interpreted then as the space-time boundary. So we don't want to go beyond that. We say that's unphysical because there are no solutions to this equation anymore. This is a subtlety on how.
So this is the place where where phi becomes imaginary.
Yeah, exactly.
Okay, but this happens. Like, I mean, this happens in like phi is close to zero and imaginary, right? Or sorry, it's.
So sorry.
But it's not a point where the space-time volume goes to zero, or is it?
It is. Well, in the end it's a point where the space-time volume goes to some constant.
I see.
But the actual space-time volume we interpret as actually this volume minus this constant. So in some sense, in this sense, it would go to zero. But this is for large M, this is a very small correction, so to say.
Okay.
Maybe you see this a little bit better here. Like when I again go to a Kruskal diagram. So here this was the original classical one. So now if we add this quantum correction, how does it deform? So again, we have this x plus x minus coordinates here. And now we are getting this line here, which I was talking about. This is the line that omega equals this critical value.
Yeah.
And here as well. And then one says that like, okay, the actual physical stuff is going on the right-hand side here. And we don't consider this stuff on the left-hand side. So that this is actually our physical space-time boundary in these coordinates.
Okay.
And here phi and omega have a unique relationship in this region. So yeah, again, we have this stretched horizon here, meeting with the singularity at some point. And now we have, again, this infalling matter shell at this coordinate, and it will create the singularity at some point, which will evaporate and go away. So this is basically the outcome of these equations here. Yeah, and now related maybe to your question, now if you would take this time, which is asymptotically flat. So this is in analogy to the Schwarzschild time, so that if you go to these coordinates and you would go asymptotically far away, then you would have a flat, manifestly flat metric. And in these coordinates, which are straight lines here, well, not actually from here, but from here originating, then I'm just telling you now, you won't see it from the equations, but I'm just telling you that if there is some guy here outside that is measuring the Hawking radiation, then he would see it essentially switching on at this time. Okay, this is what I was saying earlier. So this guy would conclude that the black hole is created at that time because he sees the Hawking radiation. Okay, so now we have two times here. One is t equals t2, and one is t equals te, where now I say t2 is the black hole creation time, and te is the time the black hole is evaporated. So this gives us a duration, a lifetime black hole of a lifetime of the black hole, basically. And so now I want to do the computation again. And so I ask before, so what do we actually expect to get? So if this C equals volume holds, if this is really true, then there should be at least a regime, maybe not everywhere, but there should be at least a regime where this volume growth is actually proportional to the black hole entropy times the temperature. Now, what does that mean in this semi-classical case? It means that, so in this model, we have actually, that's a peculiarity of this model, that we have a constant temperature 1/2 pi, which does not depend on the mass. So in particular, the Hawking radiation does not see how big the black hole actually is. And we have the value of the black hole.
Sorry, is it
yes?
artifact of dimensionality, or what's the reason why t equals 1/2 pi? Like
so you can just calculate the expectation value of the energy momentum tensor basically out very far away in appropriate coordinates, and then then it would look like a constant temperature. This is basically one reason why it is. I don't know if there's a dimensional reason.
yeah,
so it is actually, you have to, so I set here this lambda, this length scale, this 1/λ I set to 1. So of course there would be a lambda in here. So this would have dimensions of energy of 1/length. Okay. So, and the entropy of this black hole is given by the area of the stretched horizon, and which turns out to be actually proportional to the mass, to the current mass of the black hole, so to say. And it turns out that in this model, the area of the stretched horizon actually reduces linearly in this time we are considering. So this is an outcome of the model. So now, if this were true, that means since the temperature is constant, that we should expect a volume growth rate that reduces linearly in time, at least for some time ranges. So, so sadly, for the volume calculation in the semi-classical black hole, we actually didn't manage to do it analytically. So we did some numerics there. But on the other hand, we will soon be, so we also cared about the complexity equals action computation, of course, which I'm not going to talk today, but there it is actually possible to do an analytic continuation. So that should be a very, very promising future remedy of this. So, but okay, we have to do numerical calculations. So what is the outcome of those calculations? So now what you see here, let's concentrate maybe on this graph. So on the x-axis, there is the time again, and t equals t2 was the time associated, how I defined it before, like what we interpret as the black hole creation time, and t equals e is the time which is associated to the black hole, the evaporate, so the lifetime to the black hole. And on the y-axis, we again have the volume growth rate indicated. So so now we have m over kappa, which is basically n. So we said before that in order for this model to make sense, we need m over n to be actually large. Now we can just, since we can also just do it for m over n not so large and see what it happens there. And there we see this behavior here that before this creation time, so there will be some onset of complexity growth. And there it essentially goes to m over 2, which is the same value we would get in the classical case. And then there is some time which it actually needs to settle, which coincides with the corresponding scrambling time actually of the black hole. And after that, we observe that it actually goes on linearly for quite a while until the end. But as I said before, the end, we don't really, we cannot interpret much about the end anyways, because this is exactly the region where our volumes will go through regions with strong quantum corrections. So we have to kind of be agnostic about that. But so we see in particular, as we crank on m, if we increase m, this picture will look better and better in the sense that we have this onset time, and then almost immediately, so after the scrambling time, this growth will actually settle in a linear way, which is followed a very, very long time until some time which we cannot talk anything about, basically. But what happens is it matches very nicely also that if we were to extrapolate that line here, that we will actually reach zero growth when the black hole is evaporated.
So what's the slope of this linear growth? Or sorry, linear decay of the rate?
Yes. So the growth is basically also well, it basically tells you how in this particular case how much Hawking radiation goes out, basically, because so the mass of the black hole reduces linearly with the Hawking radiation. Since the Hawking radiation doesn't depend on the mass at all, at any time you will have the same kind of amount of mass losing. So that is basically why we have a linear reduction in the black hole horizon. This would be the interpretation. If we were just to calculate, so this would be proportional to n, because we have n channels which we can evaporate into. This would be the interpretation of it. Yeah. Does this answer your question, or maybe not?
Oh, sorry, I had it muted. Yeah, thanks.
Ah,
yeah.
Okay, good. Okay. Okay. So yeah, we also see we can just for fun plot it for m over kappa very small, which actually doesn't make much sense anyways, but we still see there's this onset here, and then there's something happening, and then, okay, there's almost no linearity in this region, which we actually care about. So it doesn't really work for these cases. But there where we should expect it to work, it actually kind of surprisingly works out. So in this case, there is a regime where the volume growth actually gives you S times T, which is what would you expect from from complexity growth. And as I said before, now this is numerical results, but we will actually soon be able to speak about some analytical results about that as well in the CA computation, complexity equals action. So to conclude, basically, I think there were like 3 main lessons learned in this exercise, namely that even so in the 2-dimensional model, we have to consider the volume corresponding to the 4-dimensional parent theory. Otherwise, it doesn't work at all. So this is something worth noticing, I think.
When you say
yeah.
it doesn't work, you mean like you don't reproduce classically the linear growth with the rate of n.
Exactly. Yes. Yeah. Input. Yeah, that's what I'm saying. So it does not behave. It does not go into some linear thing at all. Also, the qualitatively the curves look also much different than the curves. Like if you go back to this picture, now these kind of volumes, they are looking like this. Whereas you go on, these will further increase into the black hole. Now, if you actually were to consider geodesics, they would more like look like start here, go up like this, and go down like here again. So there's something weird happening with those kind of lines, basically. Yeah, the second point was, again, that so for the late time behavior, it didn't really matter where we chose to be, where the anchor curve was chosen to be. But in order to get the correct switch on time, which we, of course, what is correct and what is not is kind of up to us, I guess. But to get the correct one in our sense, we actually want to consider the stretched horizon as the anchor curve in order for us to being able to say that the complexity growth actually switches on when the black hole is created and not arbitrarily long before, basically. And taking these lessons learned here and taking it to the semi-classical case also leads to very good results. Good results in the sense that actually this proposal as C equals V still holds, I would say, even in the semi-classical case. And let me conclude with that. Thank you.
Thank you. Thank you, Lucas, for the very nice talk.
Thank you.
We already had a few questions, but are there any more?
So I might have missed that, but or is there a physical principle that determines the stretched horizon, or was it like formal definition?
Well, I mean, I actually have to refer to you probably to this paper in '92, where they actually defined the stretched horizon for a very good reason, probably. I don't know, is Laurus in the audience, actually? I don't see who is in the audience, so, well, okay, if he's not here, then, yeah, I mean, for sure there is, but I cannot really tell you what their main reason was to actually create this stretched horizon. Sorry.
I have another quick question regarding precisely the stretch horizon and matching with the anchor curve. If you know, go back to the classical static case.
Yes, this one, or the static, this one?
Yeah, that one.
Mm-hmm.
So in that case, the stretch horizon matches the anchor curve, and it seems like they are given both by the condition phi equals constant, so the Dilaton field should be constant.
So yes, so this is a bit unfortunate. So it does not match. So it depends on the sigma here. So if sigma A is actually 0 in this case, then it is exactly the stretched horizon. But for any other value, it is not, right?
Okay.
So this is but yeah, but in both cases, in this case, it is phi equals constant, turns out to be, using the definition I gave earlier.
With the area, you mean?
Yeah, exactly. Yeah.
Okay.
So that is not quite true actually in this case.
Right.
Because it is true in the region after the shockwave came in, but this is actually not true in this region, because in this region, this guy is still defined as being phi equals constant.
Mm-hmm.
And this guy is then just defined by this formula, which is not, in this region is actually not phi equals constant anymore.
Mm-hmm.
And this is also the reason why you have this kind of shape here and not a sharp onset, basically.
Okay.
Because they're a little bit different in these regions.
Okay, thanks.
Yeah.
I have one more question here from faraway Canada. So have you maybe you said something about it earlier? Have you contemplated doing the same exercise but with action?
Yes, we are almost done with it, not quite. So we will have something to say about that soon. But it also works very well.
But do you get qualitatively similar results, or there's some major difference?
Yes. So in the classical cases definitely, but so in the semi-classical case there are some technical issues we have to iron out before we can actually make a definite statement, because there are some ambiguities in how you actually define your action in this case, and usually in the static cases these ambiguities don't do much because they basically go away if you just consider the growth. But it actually turns out that in a dynamical case these particular ambiguities could actually do something drastic to the result. So we have to be a little bit more careful there.
I see. Okay.
Yeah.
And like one more naive question. So when you were evaluating the volume, you were calculating the length of the geodesic, but then you had weighting factor e to the minus 2 phi, right? That originated from the Kousa-Klein reduction from higher number of dimensions, right?
Yes.
Mm-hmm. And I understand that the phi term has some non-trivial radial profile, right?
Yes. Mm-hmm.
But on the other hand, like this volume is, I mean, the volume is dimension full, right? So, maybe I didn't get the essence. So the problem was that if you didn't have like this e to the minus 2 phi, then you would not get the linear growth, or you would not get the linear growth of the right coefficient.
No, I would not get linear growth.
Oh, okay. So it was really special. Okay.
Yeah. Exactly.
Okay, very good. Thanks.
Are there any more questions? Well, if not, then let's thank Lukas again.
Thank you.